Yes, as James said, I kind of made this talk up very quickly a few weeks ago, based off of some ideas that I've been throwing around for a while, and it's actually a subset of another talk that I gave last weekend. So it is slightly rehearsed, just not quite to the full extent that this is. And yeah, we're going to be looking at math.
American.
Math. Yes. I am today.
There's an X.
No, there's not. For the probably one person here that hasn't seen me present before, I'm Aaron. This is going really well. You'll find me on Twitter at Slace, and I'm a Redify senior consultant. And a few months ago, I was at the JSConf AU down in Melbourne, and there was a talk given by a guy there who has studied some parts of mathematics at university, and it was a really interesting talk, like a real crazy dive into a branch of mathematics called Surreal Numbers. The code that we're going to get through at the end of this talk is based off of the code that he wrote in JavaScript. I ported it to .NET, but it's probably not really implementing surreal numbers or anything like that. I've never studied mathematics other than one entry-level unit at university, so I'm by no means a mathematician here. This was just a talk that I found really interesting, and based off of that, I went away and did some coding of my own and came up with this kind of crazy idea that has now become a talk. So what I did was I wrote my own number system. Yeah, so part of his talk was he was talking about this concept of surreal numbers, and there's no way to represent surreal numbers in most programming languages. I'm sure there's like one programming language out there that previously did it. So he wrote surreal numbers with inside of JavaScript. Now, surreal numbers, for a very quick overview, it's representing numbers without the characters that we use to represent numbers at the moment. So you think that when you think 1, you think this thing that looks like a straight line, and 2 has got like a curvy bit and a straight line across the bottom. But numbers really, like this book here, that's 1. It's one book. So the concept of surreal numbers is you have sets that represent things. So you have sets of books on this table would be 1, and that would be represented by 1 because there are one book on this table. But so yeah, this idea of using things to represent what would be equivalent to the same numerical systems that we work with day in, day out in pretty much every aspect of our lives. So yeah, I decided that I was going to take his code, port it to .NET, and to do that, you're writing your own number system. So yeah, I mean, there's a few interesting things that you get from that, because the kind of code that I got to at the end is something like this. It's not exactly like this, but this is the base idea. So I have some way to get something that is my representation of 0. What it looks like internally and what it's stored in memory and all that kind of stuff, that's not important. It could be, but underneath it's not actually using the number system in .NET. So we get something that represents 0. If I increment that, I end up with something that represents 1. If I increment that again, I can represent 2. If I add those together, I should be able to somehow convert that to something that is equal to the number 3 in the integer system in .NET. Still with me, guys? Cool. Haven't lost anyone yet, which is a good start. Yeah, so one of the reasons why I wanted to use .NET for this is we get really cool stuff with operator overloading, whereas in JavaScript you have to write all these methods that called plus and subtract and stuff like that, because you can't actually overload the operators. Here I can overload the operators, so it just looks like working with normal variables, but we're really not, and destroying the memory of our machines. So when you write your own number system, you need to do your own equality. How do you compare that two things that you say are both 1 are 1? Or how do you say that 3 is greater than 2? Pardon? Well, yeah. So you've got to override the equal operator, but you've got to implement something internally of that says that these are equal, that these are representing the values that you want. I mean, you can even go as far with .NET to say, like, if I had my surreal number that represents 1, and I do an equality comparison to the actual integer value of 1, I should be able to assert that that returns true. Hey, you have to do your own equality. You have to implement your own addition system, subtraction, multiplication, division. You've got to basically implement your own elementary arithmetic, and this is what I didn't kind of expect to do going out. We all know what happens when you add 1 and 1, you end up with 2. But what happens to those two things that represent 1 and 1 to get something that represents 2? That was what I found really interesting, an exercise to do. But let's start with something simple like equality, making sure that two things equal. So when we do probably, like I said, I wrote these slides in a very hurried manner, so there's probably spelling mistakes all over the shop. Okay, so when we do something that is an equality statement, so something is equal if it's not less than and it's not greater than the thing that you're comparing it to in terms of numbers. So 3 is equal to 3 because it's not greater than 3 and less than 3 at the same time. It means it's got to be equal. What happens if it's not? Well, then the compiler will fail because I'm not comparing two things in my own made-up number system. So this is comparing things in my own made-up number system, not just representing Jason to Phil here. I'm not sure if they're equal or who's greater than. That's going to get awkward later. Okay, so let's say greater than or equal to. That is anything that is not it is not less than the current value. If it's not less than this, it's got to be greater than or equal to it. So greater than is when it's not less than and it's not equal to. So really, it all comes down to just various ways that we use less than and equal to. So the different ways that we can represent these and the different ways we implement these is how we can ultimately determine whether or not a number is equal to another number or whether it is greater than another number. So I think the next slide was, yep, show me some code. So we'll jump over to my code. It is all on GitHub. If you really want to dive much deeper into how your own number system works beyond what I'll be showing you in this, you can have a look at it on my GitHubs. So I will start with is equal to. So is equal to, I haven't implemented the operators for this. This was originally from the JavaScript source material that I was working with. So that's when so something is equal to when it is both less than or equal to and greater than or equal to. Because the less than and the greater than kind of cancel each other out and then makes them direct equality. So then, we can go greater than or equal to is when it is not less than, when the right-hand side is less than or equal to the left-hand side, and then ultimately we get down to the actual less than or equal to value. So me and them represents me being the left-hand side of the operator, them being the right-hand side. So I just kind of create a couple of temporary variables for this. And the first thing that we want to do is work out is either of us on the left-hand side of 0 as a value itself. So I've got a way of checking whether or not my object is the value of 0. But if I'm a negative value or I am 0 and they are a positive value or 0, then I'm either less than or equal to. So I can immediately I can do some kind of fail fast stuff here. I don't have to do all the complex logic that you would normally do to do that kind of equality check. So if I'm a negative value and they are 0, I'm less than them, which means I'm also I'm both less than and equal to them at the same time. If I'm 0 and they are positive, then I'm still less than them. If I'm 0 and they're 0, then I'm equal to them, which means that that's 3 ways of representing equality, so I can easily fail out. Whereas if I'm positive or 0 and they are negative or 0, you should never have the 0, me is 0 and them is 0 on the second if statement, because the first one should have caught that. But if I'm positive and they're negative, then I'm greater than them. So I'm not equal to them, I'm not less than them, so it means that I can fail out at that point. And then basically what it becomes is a race to who gets to 0 first. Whoever gets to 0 first is the smaller of the two numbers. So what we do is we check if we're both positive numbers. So while we're both positive numbers and neither of us is 0, we'll both decrease our value. Whoever gets to 0 first, so if the left-hand side is 3 and the right-hand side is 2, we subtract 1. Then I've got 2 and 1, I subtract 1 again. 0 on the right-hand side, which means that they're 0, which means that I'm greater than them, which means that I'm not less than or equal to the value. So it just comes down to subtracting 1 every time and just doing that in a loop until we get to 0. if we're both positive values. If we're both negative values, it's a race to 0. Whoever gets to 0 first is the greater of the two values. Still with me? So this is what I started finding out, is that I was like, wow, actually that's how you do equality. And the various types of equality that we want to do is it really just comes down to +1, -1. Really what it is. Oh God, yes. This is horrendously inefficient. You should never write your own number system. It's a very bad idea. Like, computers are really good at dealing with numbers. Let me just put that one out there. What this is more about is kind of the thought experiment that you get out of doing that.
You didn't run this on the GPU?
No. I actually tried to do count up to so. Because I'm not using the number systems built into .NET, I don't have the same restrictions in terms of representing int.max value. I don't have int.max value because my max value is represented by the amount of RAM I can throw at it. So in theory, I could create two things that both were derived from int.max value, and then I could add them together and still have something that is completely useful inside of my application. It's not really going to be useful because it's going to just destroy the memory. I tried to do int.max value +1. After 6 hours, I decided to terminate the program because I really wanted my RAM and CPU back. So yes, it's really, really inefficient. But it kind of gives you an idea of what the machines are doing kind of at the very lowest of the levels when you think of it at a high level.
On the topic of inefficiency, you could replace your while loop with your first.
Yes, this is yeah, just so you can hit a Stack Overflow exception, we could do it recursively. But no, see, what you would do is you would actually do tail recursion, so you don't hit the Stack Overflow exception. I have wanted to port this to F# because it should be so much more functional. I just haven't had time, and I've got better things to do than write a number system twice. Okay, so that's pretty easy. Like, that's how we can represent greater than, less than, equal to, and the combinations of those operators to make two things that are supposed to be numbers represent the size of the equations that we want to do. And really all it comes down to, whoever reaches 0 first, whether we're coming at it from the bottom up to 0 or coming from the top down to 0, whoever gets to 0 first is the bigger number or the smaller number, depending which direction you've come to, and that is what you can use to determine the size of the equality. So let's do math. Math. Well, we're going to stick to.
It's okay, you added the S to do.
So, in terms of it's surreal math. We're going to be talking about elementary arithmetic. So we're not doing powers of here. I don't really deal with fractions particularly well. Not going to do a square root or like an imaginary number like pi or something like that. No, we're just talking 1 + 1 sort of thing. Okay, pi, sorry, pi is a real number. I. We're not going to do I then. Yeah, it's imaginary in my number system because it doesn't exist.
And the cake is away.
Yep. Okay, so we all know that 1 and 1 is 2, and 2 and 2 is 4. I was trying to find a GIF from Barney to represent this, but I couldn't. I was kind of sad. But what actually happens when we add two numbers together? Do I have another slide? Okay, so we know that when we do 1 + 1, we get something equals 2. When we do 1 + -1, we get 1. I actually, when I gave this talk in Melbourne a couple of weeks ago, I had a bug in the maths that I had on my slide, and everyone was kind enough not to point that out until after the talk was completed. When we add two negative numbers, we end up with a negative number. So we've got these things that we need to kind of take care of when we're doing addition. Did I have another slide? Okay, yeah. So what actually happens though when we have this thing that looks like 2 and we have this thing that looks like 3 and we have to add them together to get this thing that looks like 5? Like what are we doing at a machine level to add numbers together? You think of the representing with piles of books. We have a pile of 2 books and a pile of 3 books, and we need a pile of 5 books at the end. Like, what is the process that you go through to achieve that? Okay, so
Just describe it.
I'm going to move the code off the screen if you're going to take a guess.
Well, if you are adding a positive.
Yep, that's basically what it comes down to. Is again, it's just a race to 0. Where is my code? Here we go. Yeah, so we have a left and right. I just again made temporary variables for these. If the right hand side is positive, while it's not 0, we increment the left hand side and decrement the right hand side. And once the right hand side of the operator becomes 0, then we're done. We've got our final value. If it's negative, then we kind of do it in the opposite direction. Decrease up and decrease the left and increase the right. And that takes care of both whether the left-hand side of the addition operator is a positive or negative value. We can take care of it in that way, because when you add a positive number to a negative number, the negative number goes up, so it gets closer to 0, beyond 0 if it passes. So yeah, it's just a while loop or a tail recursion function if that is your forte. So it's a similar thing for subtraction. We just have our increments and decrements in different against the different sides of the operator. So we decrement the left-hand side of the operator while incrementing the right-hand side. That kind of stuff. Okay, so addition, subtraction, that's kind of simple. Let's look at something a bit more complex like division. So we know 4 divided by 2 equals 2. 5 divided by 2, we end up with a fractional value of 2.5. So let's think about how division would work. Pretty much, again, it's going to be a race to 0. Let's find this. But there's a few interesting things that we need to take care of when we're doing division, such as divide by 0. And we know that when we divide by 0, well, that's going to just screw up in pretty much anything. So the .NET framework gives us a divide by 0 exception.
Make them one of your imaginary numbers. It's like fun.
We also know that if the numerator is 0, then the value that we want to return is 0, because 0 divided by anything is always going to be 0. I also learned that the remainder is actually called the value that we return as the result of the division is called the quotient. That's something I learnt doing this. I knew the numerator and denominator. I was sure it had a name. I just didn't care what it was. Quotient, whatever. I'm not a mathematician or anything. Mathematician. Okay, so if the denominator is a positive value, while the numerator is still a positive value, we subtract the numerator from the denominator, we increment the Q word. And as soon as we hit 0, we kind of that's when we bail out. And whatever we have left over on the numerator, that's our remainder value. I think this has actually got a bug in it. I'm not dealing with remainders particularly well. I've got a JavaScript function around that does this better and deals with remainders, so you can get fractional values and stuff like that. But yeah, so again, it's just a race to 0. This all works because all my unit tests pass. For anyone that's like, haha, there's a bug. No, my unit tests pass. Snap.
Unit tests are great.
They are. I may have fixed a couple of unit tests while writing this talk, but that's beside the point. So yeah, again, it's all just a race to 0. And because I've got operator overloading here, I'm actually just using my implementations of addition and subtraction to increment and decrement the numerators and all that kind of fun stuff. I could, instead of using this increment and decrement function, use the double plus and double minus to do that, or I could do +1 -1, plus a value, my surreal number representation of 1 minus the surreal representation of 1, and all those kinds of crazy things. But I just wanted to stop writing this imaginary code. But yeah, again, all comes down to a race to zero inside of while loops. And that's how you divide numbers together. But did anyone see why you wouldn't be able to divide by zero? Bring the code back up again. So why would you not be able to divide by zero? Correct. You were never able to get to zero. I'd always taken for granted why you had divide by zero exceptions, because there was like math said that I couldn't divide by zero. But until I had to implement division myself, I didn't quite understand. I'd never taken the time to understand why a divide by zero exception happens. Because if you were to subtract, say we did 1 divided by 0, so the numerator is 1, we subtract 0 from that, and then the numerator is still a positive value. So we subtract 0 from it again, and it's still a positive value. We subtract 0 from it again, and we end up in an infinite loop. We can never reach 0. So that's why we can't divide by 0. I'm sure that there's particular versions of mathematics that says that there's different reasons why you can't divide by 0. To me, the reason you can't divide by 0 is because you'll never be able to represent number. It's an infinite value because you can never get to that point. And that's how we do math. It comes down to +1, -1, and we do that in different kinds of loops, depending on whether we're just adding or subtracting values, whether we're dividing values, whether we're multiplying values. I did actually have a toy around with doing power ofs, and power ofs are just loops around multiplication. Doing power of roots was something that my brain started to melt, trying to conceptualize how that actually works. But again, that'll just probably be some kind of loops and probably off division. I think that was my guess, and I was like, yep, I'm done. But I thought it was quite beautiful. It was really eye-opening to sit down and do something that, since primary school, I've been able to add 1 and 1, and then by secondary school, I could times 1 and 1. But sitting down and actually seeing what happens at a kind of lower level with these chunks of memory or chunks of whatever I want to represent them as, that how we can get to these integer values that we have in programming libraries. It's also utterly pointless. Seriously, as I said before, computers are really good at doing number stuff. Writing your own number system is very, very slow. After 6 hours, I decided I actually have no idea how close to int.max value I'd gotten after 6 hours, because I don't have any way of kind of peeking inside the box that represents my my surreal value. And so, I don't know where I got to after 6 hours. But at the end of the day, this was just a lot of fun. I started writing this before I flew back from Perth at Easter. And I sat there on the flight and just kept hacking away at this. And this guy was sitting next to me. I saw him looking at my screen and started talking to him. And he was a software developer. It's like, oh, yeah, I'm writing my own number system. And you could just see he's like, I need to get off this plane now. But I had a hell of a lot of fun really learning how, at a very raw level, moving these things that represent numbers around and what happens in that space. That's all I had time for today. Thank you for your attention and for the additional S's on math. I would say I will take questions, but that's probably going to end very badly for me.
No, what did you do with your data structure for the number itself? Why did you chew up so much memory?
Okay, so the data structure, so a surreal value, if I just bring up Notepad in, so it kind of looks like this. So that's 0 in surreal numbers. If we were to go, so that's 1. So we've got a set to the left-hand side of, the right-hand side of 1. If I was to put it on the left-hand side of 0, then now I've got negative values. Then if we go like that, so that's like -2, and then basically the way you build up. Yeah. what is it essentially a set of empty arrays. So that's what I've been using internally to track these is empty arrays. And that's kind of, why your memory blows out, because I keep reallocating the arrays. And it's not properly functional, but if you were actually writing this in a functional programming language, I think you'd probably blow out your memory even quicker, because you probably wouldn't blow it out any quicker, because increment would create an entirely new version, whereas at the moment I keep manipulating that array structure in memory, so I keep having to reallocate the amount of memory space represented by the array as kind of value goes out. Yes, it probably has a lot of relationships to lambda calculus and stuff like that. Not really a mathematician.
Stuff that like giving this and this, but not really how these things work. Really great pieces.
Oh, I'm sure that someone has written a proof on how greater than and less than works. So I really hope someone has, because otherwise, a lot of computer people are just going, "Yeah, we'll just do it that way. Should work."
But yeah, you might like exact translation from that sense.
Dun dun dun. But probably not, because my code's not particularly. Oh yeah, I need to grow a bigger beard. Yeah. Any other heckling or questions? Yep. I don't know. What is it? What is it short for?
American.
Well, I have a math object in JavaScript when I'm working with it. And yeah, that's why it's math.
It's written by. Any other questions outside of this debate? Only I can do this.
All right, and on that note, I am going to stop my recording. If I can work out my shortcut key.
Thanks, Aaron.